Hey guys, today we're going to do an episode on circular motion. Um, right, so the first thing we're going to do is derive the circular motion equations. So if you have a circle and you're traveling around it, there's this angle theta, this arc here, which I'm just going to call S, and a vector V. So our angular velocity is going to be defined as omega, and it's the change in angle over the change in time, d theta over dt. So from geometry, we can know that theta times r is equal to our arc. And we also know that this arc is going to be equal to our velocity times the change in time. So the velocity times delta t is equal to the change in the angle times r. And so we can rearrange this to get d theta over dt. So the change in angle over the change in time is going to be equal to our tangential velocity over the radius. And if you make these very small, you can get d theta over dt, which is equal to omega. And that's our angular velocity. The next thing we're going to do is derive angular acceleration. And how you do that is, well, first I'm going to define it as alpha. And alpha is going to be the change in our velocity over the change in time. So we already have an equation here that has a bit of delta t in it. So we have the change in angle times r is equal to our velocity times the change in time. We can use this equation as well as another equation. So we can, since the length of the vector is constant, and when we go around the circle, only the angle of this vector is changing and not the length. So we can say that the change in angle times velocity is equal to the change in our vector, delta v. And so we can rearrange this to be delta v over delta t. And if you do the math, you'll get the angle, v squared over r. And that'll be your tangential acceleration. Now the last thing for us to do is get centripetal force. So we have F equals ma. And instead of a, we're going to use our angular acceleration. So we have F equals m times alpha, which is going to be equal mv squared over r. And so that's how you derive the circular motion equations. So next we're going to do a bit of an example problem. So I'm going to do is erase this derivation and rewrite them over here so we can have them for reference. Right, so for centripetal, going to be mv squared over r. Omega is equal to v over r. And make sure I put these vectors here because there's a direction associated with that. Here it's always tangent to the circle. There could be cases where it's not tangent, but in circular motion we don't really need to worry about that. This is just to be clear about what it is. Right, so alpha is equal to v squared over r. So the example problem we're going to do today is banked road. So let's say you had a road and it looked like this. It was circular and it's got some radius r. Sorry, my mic cut out there for a second. Right, so And the road is at an angle here, theta, and there's a car driving along this road. So it's kind of like one of those banked roads. So I'm going to try and do this in like the least confusing way that I can. So I'm just going to redraw the car as a dot so it doesn't get in the way. So if we do our free body diagram, we can get N, our normal force here is tangential to the, oh, not tangential, is normal to the road. And so we also have gravity here, mass times gravity. So I'm going to use a different color for this. Oops. All right, so we have our components of the normal force here. There's the vertical component, and then the horizontal component. Because of how similar triangles work, we know that this angle here is going to be equal to theta. And so this vertical component is going to be equal to the normal force times cosine of theta. And then this horizontal one is going to be the normal force times sine of theta. And so we want to get a formula. Oops, I put a little parentheses there. That's wrong. Okay. So, right. So we want to find an equation for this angle here and see if we can't derive a relationship between that and the centripetal force. So these vertical forces have to cancel out in order for the system to be in equilibrium. So that means that our n cosine theta is going to be equal to mass times gravity. And also, this horizontal force is going to be the same as our centripetal force. They have to be equal. So our force centripetal is going to be n sine of theta. But from here, we know that force centripetal is also equal to mv squared over r. So from this, we can derive a relationship. All we have to do is divide this equation by this equation. And so we end up with n, oh sorry, we're deriving this equation by this equation. So it would be n sine of theta divided by n cosine of theta is equal to mv squared over r, hopefully I don't run out of space, over mg. These m's cancel, and then you get v squared over r times g. And so these n's here will also cancel, and sine over cosine, from a trig identity, we can say that it's equal to the tangent of theta, and that is going to be equal to v squared over r times g. And there we go. And that is the relationship between the angle and the velocity. So it should be noted that there's no mass dependence on here. So it doesn't matter how much the car weighs. The only thing that matters is the angle and how fast it's going and the radius. Gravity is constant. Well, the radius is constant too, but you can build a road with a different radius. So yeah, thanks for watching. Bye.